All right, this is the Nature of Science section where we talk about resolution, accuracy, precision, and errors. So just to start off, if we're looking at height, right? If you're looking at this photo, what height do you think this photo was taken from? Like, what would be a good guess? Do you think 10 feet would be a good guess? Probably say no, but this photo was taken at too high of a height to be 10 feet. What about 10 miles? Well, 10 miles would be too high. I know it wasn't taken from 10 miles. Would 500 feet be right? Yeah, I'd probably say so. Now let's just say the helicopter went up another foot. What would your guess be? Like, would you be able to say 501 feet? Would you be able to accurately say that? What about weight, right? So if you looked at Mr. Cardoza and you said, how much does he weigh? Like, what would a good guess be? Like 100 pounds? Probably look at that and say, no, that's too small. What about 500 pounds? That's definitely too much. What about 180, right? Yeah, maybe that'd be a good guess. Now, let's just say you guessed that in the morning and then you came back in the afternoon after I had a large lunch. Would you be able to say, yep, he weighs 181 pounds? Could you be able to tell the difference between 180 and 181 pounds? Here's a last example here, right? How many people do you think are in this crowd? Like, what would a good guess be? Like 500? Probably say there's more than 500, right? Maybe 50 million. We probably look at that and say that it's not quite 50 million people, maybe 500,000. Yeah, that might be a good guess. Now, if one person from this crowd went home, like what would your estimate be? I mean, would you be able to say 499,999? Probably not. You could not tell the difference if one person left. So in all of these examples, you were doing the measuring. Now, if you wanted to be more accurate, you probably need better instruments, or you wanted a better resolution, you need more instruments, right? So like if you wanted to measure the height, you probably look at the altimeter on that helicopter that took it. If you wanted a more, if you wanted to be more accurate with the weight, you'd probably want a scale. And if you wanted to be more accurate with the crowd, you probably want a turnstile, right? You probably want a turnstile. All right, so that brings us to resolution, and that means the smallest interval that can be measured by an instrument. So if you look at the top, well, that's just a meter stick, and it doesn't have any marks. It would be, the smallest division would be 1 meter. Now on the bottom, it's divided into 10 parts. So that means the resolution would be 0.1 meters. That's the smallest that this instrument is divided by. So if we look at this example, the resolution of the stopwatch would be 1/100th of a second, or 0.01 seconds. The resolution of, let's look at this one, right? So this one's a little bit tricky. The resolution of the scale, well, each one of those dash marks, well, it's not going to be 1 gram, because if we get to that halfway point between 0 and 20, that'd be 10. You'd have to count by 2 to get to get to 10 by the halfway and then get to 20. So each one of those dash marks is 2 grams. Now let's talk about the uncertainty, or that doubtful digit. Now, just because the resolution of an instrument limits our exact knowledge of a reading does not mean that we cannot estimate a measurement with a higher resolution. We call this level uncertainty, or doubtful digits. This can only be done with analog instruments. So what that means is that if we look at the resolution of this meter stick, it'd be 1/10 of a meter, 0.1 meter. But could you make an estimate to that next digit? Like, could you look at this and say, well, it's 0.1, 0.2, 0.3, 0.4, maybe 6, yeah, 0.0, maybe 0.46 meters. That'd probably be a good estimate. So we could say the first digit 4 is certain and the second digit 6 is doubtful. We thus have two significant figures in our measurement. That's what's going to affect it. We have to include those uncertainty digits because of those significant figures. So this can only be done with analog instruments. So you can tell if like that reading is in between that. But let's just take a look at something like a stopwatch. Well, it goes to the 1/100th of a second, but there's nothing to look at to see if you can make an estimate. That's it right there. That's the resolution. But we can extend our significant figures with the analog instruments by being able to estimate in between. So why do we do this, right? Like significant figures. Significant figures are the number of digits in a value, often a measurement that contribute to the degree of accuracy of a value. So when we're in the science class, we need to know which one of those contribute to that accuracy of that value. So let's take a look at how to figure out which digits are significant and which are not. 1 through 9 are always significant. They're always going to be significant. Now, the zeros are the tricky part, right? So leading zeros, the zeros in front are never significant, just like in a decimal point. Now, captive zeros, the one in between significant figures, are always significant. Now, trailing zeros are the tricky ones. Trailing zeros are only significant figures if there is a decimal point. So you can see there on the example on the right, that trailing zero is going to be significant. We measured that, but on the left, that trailing zero is not. That is a placeholder. So here's why they're important, right? So if we look at this one, let's take a look at this one, right? Let's just say you were looking at me and said, okay, you weigh about 180 pounds. Now, is that zero accurate? Right? Are you like, could you say that, yep, he weighs exactly 180 pounds? I know it's 180 pounds, but could you tell the difference between 180 and 181? Probably not. So if we use our rules, you look at these and you would say, well, that trailing zero, right? So 1 and 8, well, I have two significant figures already. Well, the trailing zero, it does not have a decimal point. It is never significant. So this one has two significant figures. Now let's just say I step on a scale and it says 180.0 pounds. So let's take a look at that. I know 1 and the 8 are significant. Let's look at the trailing zeros. Well, there is a decimal point, so those are significant figures. This has four significant figures. That's the difference. It has to do with the resolution of that instrument. Just looking at somebody saying about 180, that zero is a placeholder, but stepping on the scale and it's saying 180.0, well, those zeros have been measured. So same thing if you're looking at a crowd. So if you're looking at 10,000 people, yeah, there's about 10,000 people there. That is one significant figure. But if we look at 1,001 people, well, I know the 1 and the 1, those are going to be significant. So I already have two, and those are captive zeros. So this one has five significant figures. So if we're looking at this one and it's like, that's a turnstile, that counted 10,001 people. Those are accurate digits. But just saying about 10,000, you don't know if those digits are accurate, right? So that's the difference there. And this one has an example of all of them, leading, trailing, and captive zeros. This one has five significant figures, right? That zero, that trailing zero, is going to be significant because it is in a decimal point. Now, the reason why it's important, adding or subtracting, yeah, that's going to be important. It has the same number of decimal places as the number with the least number of decimal places. But where it's important more so, at least in a physics class, is when you multiply or divide numbers. Round the result, right? So the same number of digits as the number with the least number of significant figures, the least precise value in terms of multiplication and division. So if you look off to the right, if I have a number like with 3 significant figures being multiplied by a number with 4 significant figures, well, my answer, I have to round that to the third significant figure. Now, here's the example that I use. Let's just say you're going to go outside and see how fast somebody can run a 100-meter dash. You get outside and you forget your measuring tape. And you say, okay, I'm just going to estimate about how far 100 meters are, right? I'm going to estimate how far that is. And you know about how far 100 meters is. But then on your mark, get set, go, you have somebody run, or you run, and you have a stopwatch, right? So 13.63 seconds. So yeah, that has 4 significant figures there, but we can calculate the speed. I want to see how fast I ran this 100 meters. So obviously, I just take 100 meters divided by 13.63 seconds, and I get this number. But here's the thing. Where on this is accurate and where on this is just mathematical numbers, right? Because we know that we can be accurate to some degree. But how accurate? And that has to do with the least accurate instrument. And it was you just eyeballing 100 meters. That's probably just one significant figure, right? You probably just have one significant figure. So even though my stopwatch has a resolution down to the 100th of a second, well, that last one doesn't really mean much because just eyeballing 100 meters doesn't mean that 3 was right. So if I'm doing this, I could say maybe about 7 meters per second, right? That would probably be a better answer, one significant figure, because I just eyeballed 100 meters. So let's take a look at what this means, right? So let's take a look at this one. Let me just move this. You can see that it's 100 centimeters across. So if you record the length, the resolution is 100 centimeters. Now, it does have an uncertainty digit because it is an analog instrument. Now, using that instrument or using that information, how long would you say the line is? I'd probably say about 30 centimeters, right? Maybe 20, maybe 30. I couldn't say 30.287456, right? I couldn't even say it's 32, but I could say it's about 30, right? Based on that information. Now remember, if we use those rules, this only has one significant figure. Well, let's take a look at the same line again, but let's increase the resolution here. The resolution now is one or is 10 centimeters. And it does have an uncertainty digit because it is an analog instrument. Now, if I'm looking at this, I would probably say it looks about to be 23 or 22 centimeters. That's because it does have an uncertainty digit. Now, if we look at this information, it has two significant figures. So I'm increasing the number of significant figures with my resolution. So let's take a look at this last one. Okay, now I can look at this one. Now the resolution is going to be 1 millimeter and sorry, 1 centimeter. But I could make an estimate because it does have an uncertainty digit, right? So I could say it's about 22.5 centimeters. It's somewhere in between 22 and 23 centimeters. So I would say about 22.5 centimeters. And this answer has three significant figures, right? So as I increase the resolution, I also increased the number of significant figures. So what's the difference between accuracy and precision? So if I'm looking at an experiment, the accuracy of an experiment is the measure of how close the experimental results comes to the accepted or actual value. So think about a dartboard. Accuracy is represented by how close the darts are to the bullseye. So if we were taking an experiment, determine the value of how to drop an object, and I got 0.53 seconds to 0.52 seconds, right? And the accepted value is 0.51. Well, the one that's closer would be more accurate. Think about throwing a dart. You're trying to hit that bullseye. You're really trying to hit that bullseye. So let's take a look at precision now. Precision of an experiment is the measure of its reliability, how reproducible the result is. Think about a dartboard. Precision is represented by how close the darts are to each other. So if we're doing that same experiment, I get all of these, right? So 0.63, 0.64 seconds, 0.63, 0.61, but the accepted value is 0.51 seconds. Well, notice all these numbers have high precision. These numbers are close to the desired result, but or close to each other, but not to that accepted value. So the measurements are precise but not accurate, right? So measure how consistent repeated measurements of a particular quantity are to each other, right? So think about that dartboard, how close those darts are to each other. So this is a good representation of precision versus accuracy. How close the darts are to the bullseye, that's going to be accuracy. How close the darts are to each other, that is precision. So I'll move this down here. All right. All right. So let's go ahead and answer this one. Well, what affects accuracy and precision? So errors. Accuracy and precision are affected by errors. Now, there are two types of errors that we're going to learn about: systematic error and random error. And errors do not equal mistakes. So systematic errors typically caused by defects in measuring instruments. They are reproducible. They usually shift the data in one direction, and these errors cannot be reduced by repeating the measurement. So think about this. Think about a broken scale that weighs 10 pounds heavier, right? It always gives a value 10 pounds heavier than that accepted result. Well, what it means by reproducible and cannot be reduced by repeating. Well, if I step off and I step back on, well, did that get rid of that error? No, it did not, right? I could do that all day long, but that's not going to get rid of that error. Now, these errors can be eliminated. And think about this way is that, well, you just get a new scale, right? That would be a good way to eliminate that error, but you have to identify it. So there we go. And they lead to poor accuracy. Now, another way that systematic error is the parallax, the parallax in reading. So that means like if you need to measure an instrument, like an analog instrument, you can see on that top, just like a scale, if you're reading off to the side, well, it's going to shift your data in one direction because you're going to be reading it heavier. Same thing with you're measuring something with a ruler or reading a graduated cylinder. You want to make sure you're reading those head on. All right, parallax systematic errors can be eliminated by reading the device correctly. Really easy to get rid of. All right, So if we look at random errors, there's statistical fluctuations in either direction in the measured data from uncontrollable causes in the environment. Now, random errors usually result from the experimenter's inability to take the same measurement in exactly the same way. Now, they are not reproducible, and they usually shift the data in both directions. Random errors can be reduced by averaging over a large number of observations, and this leads to poor precision. My results are not close to each other. So in order to look at all of this, we did drop the ball experiment. All right. So in this one, we did three different tests basically, right? The first one, all of them, you were trying to figure out how long it takes for a ball to fall 1 meter. Now in the first one, you weren't allowed to use a meter stick. You weren't allowed to use a stopwatch. You were doing the measuring of both. You can gauge how long something takes. If you drop a ball, you can say, well, it's not 5 minutes. It's definitely under that. You can tell about how far a meter is, or 39 inches. So you could gauge that, right? Now, the question down here in this experiment, which measurement will have the lowest resolution in significant figures? They both are. You're not going to be very accurate in doing that, right? They're both probably going to have one significant figure, like, at best, right? So you can see here the next one. You were now allowed to you are now allowed to use the stopwatch, but not the meter stick. So now you can see here, you get a little more resolution here because of the stopwatch. But like I said, you don't know how accurate this is because you will have the lowest resolution, and you are the limiting factor of the significant figure because you're the one gauging how tall 1 meter is. Now that last one, you're allowed to use both, right? You're allowed to use both. So now you're probably getting better resolution here, right? So this is probably a little more accurate as to how long it takes a ball to fall 1 meter. Now, this is a question: what is that lethal weapon 2 method? So if this experiment were to be conducted again, what would you need or procedure would you change in order to increase the accuracy? So in the movie Lethal Weapon 2, there's a scene where they have to pull someone off the toilet before it explodes and get them in the bathtub, and they had to synchronize, right? So it was like, on your mark, get set, go. Well, are we going on go, or or if we're counting 1, 2, 3, are we going on 3, or are we going go? So you had to synchronize that, right? So that was a part of it, right? Somebody was starting the stopwatch, somebody was dropping that ball. Now, there's always going to be some delay in reaction if you have two different people doing it. However, uh, you should have had the same person doing both. That way you could eliminate that, and you should get closer. You should have started that timer as close as possible to releasing that ball. Now, as far as precision, well, that's the same way. You wanted to make sure that it was from the same height. So maybe you did the same process over and over again, and if you were measuring height without the meter stick, maybe say, okay, it's going to be from my belly button or from my hip. I know that's about 1 meter. Maybe you don't know how accurate it is, but you can get as precise as possible. Get those numbers close to each other. Now, random errors, there's a lot of random errors here. There's no guarantee that you started the stopwatch at the exact same time it dropped. There's no guarantee you started it from the same height when you did not have that meter stick. Now, what we did to reduce it is average them, right? Remember, you can reduce, and it did affect the precision of that experiment. That's what random errors affect. Now let's go to systematic errors. This one was tricky because the device that you were using mostly was going to be you. Like, yeah, you're using those measuring devices, but there's always going to be a delay between dropping the ball and starting the timer. So the systematic errors are going to affect your accuracy to that desired result. Now, one question that I should ask is, well, what's the limiting factor here? And that's going to be humans. So if you were to do this experiment again, you might add like a photo gate. Look at that resolution, right? So it's down to 1/10,000th of a second. I have these at, I measured these out to be a meter, and I dropped it. But once again, I still haven't eliminated the human factor. I could have started it just a little bit. Notice my numbers are getting a little more precise, a little more accurate. But like I said, you could make this better. You want to eliminate, if you could do this experiment and eliminate humans from the equation entirely, that would be best. It would still be a little bit of random error, though, just because of little fluctuations, right? You can't do this experiment the exact same way, but that's what you could do. So, once again, there is just too much unknown in the universe to take a break from learning. Get out there and question everything.